Okay, so I'm just gonna go straight to the point. It's just asking us to complete the mechanism by drawing the curved arrow. And then we have to identify what kind of steps are involved. For example, it might be proton transfer, could be the nucleophilic attack, and we could also have loss of a living group, and finally the rearrangement. And there are many types of rearrangement, but for now we are mainly concerned with the methyl shift and the hydride shift to create the stable carbocation. Okay, so that's what we're gonna do for the second part, to answer the second part. And let's start with drawing the arrow from compound 1 to compound 2 step by step. Okay, so I see that PPH3 is attached to the bottom nitrogen. The left side is intact, and I see the removal of the positive formal charge on the nitrogen. So I'm gonna have the nucleophilic attack on that nitrogen, which is our electrophilic center. So lone pair is attacking the nitrogen to create a bond between them. And then I'm gonna push that bond. Okay, so right now I have no lone pair. Because nitrogen cannot have what's that? 5 pair of electrons, I'm gonna push that and then create a neutral nitrogen. So there gotta be a implied lone pair here on this structure. So I'm gonna call that nucleophilic attack. Okay, moving to the next structure, we have a living group as the nitrogen. So there gotta be something going on. So I'm gonna also have that lone pair around the terminal nitrogen. And looks like I need to create a triple bond by pulling the lone pair to form the triple bond between two nitrogen. Also, if you compare the structure, I have a minus charge on this bottom nitrogen. That means I need to grab that bonding between the very bottom and the middle nitrogen, and I need to place it on the nitrogen atom. Okay, there is also implied lone pair here. So over here I have a 2 pair of two lone pair of electrons. And that nitrogen is going to go away by breaking that bond. And to go to this large structure, you see we have to connect the compound 3 with compound 2. Now where do we see the relationship here? Well, we have a very nucleophilic nitrogen, and we need to attack that to create a bond between them, between two structures. And I see the relevant point is that carbon, you see, this carbon I'm talking about. So our electrophilic center must be over here. Okay, I'll also say why that is so. We have oxygen on the carbon is attached to both oxygen, and oxygens are very strong electronegative atoms that tend to pull the bonding electrons toward themselves, thus creating our carbon to be very electropositive. In other words, I'll have a delta minus here, delta minus, and this will be quite delta plus, which kind of acts like the carbocation, but it's really not carbocation. So that's why I call it electrophilic center. And let me erase that. Okay. And then, but then we cannot violate the octet rule for any second row element, Therefore, I need to create a negative charge by pushing that pi bond toward the oxygen to create the negative charge, negative formal charge, and there I have it. Oh, by the way, I need to identify this as a loss of living group. Okay, LG stands for living group, by the way. And then this is just the nucleophilic attack. Nucleophilic attack. Okay. Now, coming to this structure, to go from here to here, now notice that we no longer have the ring structure. In other words, we have to break this bond, and then also we have a double bond between carbon and oxygen right before the triangle happens there, or cyclopropane is there. So I can create a double bond between the carbon and oxygen by having a nucleophilic attack, and then I have to break that. So to break that and then create a negative charge, I have to push these bonding electrons toward the oxygen. And you might wonder, why do we have a double bond for that oxygen and why is a minus charge there? Well, there are two ways you can see this. When you break it, remember this is still single bond, and the single bond tend to have a multiple or possibly infinite number of conformation by rotating around this carbon. So it's very flexible, unlike the double or triple bond. Another is that when you have a minus charge, and this is more likely the correct explanation, when you have a minus charge there, technically when you see the molecule, you don't have that negative charge as completely located on the oxygen. What you see is that the negative charge is actually diffused through these two oxygen by having a resonance structure. So we could place that double bond here and then create a negative charge, and it's actually really diffused, so it's equally distributed. So don't get swayed by, oh, why do we have a minus charge here? They both can have minus charge, partially minus and partially minus via the resonance structure. Okay, so end of the sidebar. So coming back to this structure, let's see. So I have to compare this with this with that. Well, looking at that, I have a double bond between the nitrogen and the carbon. I see that pH3 on that oxygen. Okay, just imagine, for the ease of our explanation, I'm gonna think just they are rotated, and then that oxygen, the lone pair on the oxygen, can actually interact with our nucleophilic center, our phosphorus, and then that bond between the phosphorus and the nitrogen can actually form a double bond over here. So we're gonna have double bond, and then that in turn is gonna push our pi bond to the oxygen atom. Okay, so let's actually label this. This was a nucleophilic attack. And this is also nucleophilic attack by the lone pair. Okay, let's compare this structure with the very bottom here. Okay, cyclopropane is still retained. However, we're gonna create a ring structure between this carbon and the nitrogen. And then I no longer see double bond on that oxygen here. But I see a double bond on the bottom oxygen. So let me draw the lone pair first. Okay, lone pair here. So I can imagine this lone pair is actually forming a double bond, and then okay, carbon cannot have 5 pair of electrons, therefore this bond is going to really create the bond between the nitrogen and the carbon. Another way to visualize is, you can place it on nitrogen like we did in the resonance structure in chapter 2 and 3, and then that's going to act like a nucleophilic center to attack the carbon attached to the both oxygen there. Or we can just simply draw the bond between, or this can just automatically attack there. I mean, it doesn't really matter if you create the bond there, arrow there and another arrow, but for the simplicity I'm gonna just do the this double bond acting like a nucleophilic center, and then attack there to form the single bond between the nitrogen and the carbon. And then that pi bond need to attack, well, actually place the electrons on the oxygen atom to create a negative formal charge. And finally, from this structure to that structure, I see the difference in, now this has a living group, and this needs to form a double bond. So I'm gonna draw the lone pair bond, and then he's gonna attack or create that double bond, and then we're gonna push or break that bond between the O and C here, and you see that as a living group. You see that it's not gonna have a net charge because we have a positive charge on that phosphorus, but when they leave, oxygen has the negative formal charge, so by net sum we have the zero charge. So we have a carbon-carbon double bond, and that's what we have, and this should be correct. So let's actually identify the last two structure. So over here, this is going to be obviously the nucleophilic attack by the lone pair of the oxygen. Nucleophilic attack. And on the very bottom, to render this structure to the very final form, we have a loss of a living group. I mean, yes, some might say, oh, this is like another nucleophilic attack, but the main thing is that what trumps over is the we have a living group from our structure, so that takes the precedence. All right, that's it.